We introduce a general method for three-dimensional gaze estimation for wearable devices. The gaze machine makes use of 4 cameras. 2 eye cameras track the eyes and 2 cine cameras form a calibrated stereo pair. Eye tracking has developed in the context of studying human visual selection mechanism and attention. Early approaches address the estimation of the gaze point on screen, assuming the head is fixed. Most of them are based on polynomial mapping or regression and do not address changes in pose of the subject's head. This requirement brings the need to structure the experimental environment and the use of multiple cameras or light sources. Moreover, most of the existing systems rely on complex models of the human eye. While a great amount of research has focused on remote gaze tracking, today there is a renewed interest for portable devices that can be employed in real-life experiments in 3D unstructured settings. Visual localization of wearable devices is crucial for building paths of the collected fixations in 3D. The human eye is extremely complex. We introduce a general method to estimate the fixation point in 3D that comprises 2 steps. A geometrical model is fitted in order to recover the pupillary axis, and a suitable learning method allows the recovery of the visual axis after the calibration procedure. To overcome the limitations related to special assumptions on the eyeball or cornea shape, and especially to cope with the eye dynamics, we chose to model the locus of pupil centers as a differentiable manifold. This approach is general, although we provide an algorithm to estimate the parameters in the case of generic quadrics. The estimation of the gamma manifold is based on the definition of a set of pupil representations in space which are compatible with the pupil, imaged as the conic C. Theta is formed by the pupil center, psi, and the pupil plane, pi, which are defined up to an unknown scale factor, lambda. The pupil is imaged as the conic C by the camera P. In space, it is a circle lying on the pupil plane pi. The pupil conic back projects to a cone. There is a twofold ambiguity for the computation of the pupil plane. Pupils in space are circles. They lie on planes cutting the back projection cone of the pupil image C. Computing these planes gives rise to 2 ambiguities. The problem admits 2 solutions, which are defined up to an unknown scale factor lambda. We now turn to the actual estimation of gamma. If we assume that gamma is a quadric, 4 pupils are needed to estimate gamma parameters. Because of the ambiguity on pupil planes, 16 quadrics are candidates to the problem of finding a good initial estimation of gamma. Thus, the 16 candidate quadrics are computed from the associated polynomial system. A method is needed to identify the best initial estimation of gamma. An error measure is used to identify the best candidate quadric and subsequently refine the initial estimation. Given the pupil plane pi and the pupil center psi from the pupil representation in space, the error is defined as a function of the angles theta, defined by psi and the line joining the camera center and the point x, and phi, defined by the true and the estimated pupil plane. Once the best candidate quadric has been identified, a gradient descent optimization is carried out to refine the initial estimation. At this point, the locus of pupil centers, gamma, has been estimated. Finding the pupil axis resides in computing the surface normal to gamma in the point corresponding to the pupil center x. To calibrate the gaze machine, the user is asked to gaze at the center of a known 3D marker, while panning and tilting his or her head. After the calibration, data can be collected and the 3D point of regard is estimated in the reference frame of one scene camera. In order to collect data in a coherent frame for the experiment at hand, localization of the gaze machine must be addressed. In the video, visual localization for the gaze machine makes use of the data from the scene cameras. The collected path of fixations is shown together with the pose of the observer. Data from the gaze machine are used to design and validate dynamic models for computational visual attention. As part of the nifty European project, the gaze machine is being used to collect data in the project evaluation scenario. In the video, an expert firefighter is simulating an intervention in the tunnel car accident scenario.